Welcome back to Let's Talk Concrete. This is the part 2 of our conversation on the evolving robustness and design flexibility of structures with high-grade and high-performance concrete. In part 1, we discussed how the journey of concrete has evolved, the challenges of designing high-grade mixes, and the role of materials and admixtures in achieving performance beyond conventional limits. In this episode, we shift our focus to application, economics, durability, and future-ready solutions, addressing questions that matter most on real projects and job sites. And to guide this discussion, we are joined once again by Dr. Satish Jain, Managing Director of UHPC India Private Limited. With over 25 years of experience in structural and construction engineering across India and the USA, Dr. Jain is a pioneer of ultra-high performance concrete in India. He is also the chairman of UHPC Technical Committee at the Indian Concrete Institute and a member of the IRC subcommittee on UHPFRC. Dr. Jain, welcome back to Let's Talk Concrete. Let's continue our discussion. Sir, how important is the role of admixtures in high-grade concrete?
Well, let's talk about one admixture. When you want to increase the strength of concrete, right, there is a simple scenario. You need to actually reduce the amount of water. If you do not, you're not going to get to that strength. It's difficult. Let's not say you cannot, but it's difficult out there. So thereby, there are water reducing admixtures, there are super plasticizers. There's also the challenge of transporting concrete over longer distances, over longer time frame. So now you have, retention admixtures, right? So that you retain the workability of concrete. So those kind of admixtures are in place. Also, certain times you need concrete that gains strength, quite fast, really fast. So you have accelerating agents. So you see that the chemical industry over the last couple of decades has really evolved, pushing all these new generation admixtures that go along with your concrete. There was a time when you initially spoke about 1:2:4 concrete, there was zero admixtures. It was just about water. But today, it is the chemical admixtures that is making high-grade, high-performance concrete possible all around the country and the world.
Sir, how do we balance the rheological properties in high grades?
Okay, again, when we say rheology, we are really talking about some basic words like flowability, like workability, like pumpability. And in that sense, for a layman, what is workability? That means I'm able to work with concrete over whatever time that I am placing concrete, right? So if you are able to work with it, there are parameters like a spread test or, your cone test, which is there to test your workability. That's one aspect of it. So you got admixtures, etc. again, to help increase your workability. Also, when I say the rheology in terms of pumping, how high do you want to pump? How high can you go? Maybe how long can you go horizontally and how high you can go. So again, it's the chemical industry, that is working really well towards that. I'll give you an example of Burj Khalifa for that example. That almost the top 40 stories of the structure is not concrete, whereas the entire rest of the building is concrete. And that is because at some point of time, they were not able to pump concrete up. Right. So the top 40 stories is pretty much built in structural steel. So that's the difference. So concrete has to be pumpable. Now that was really high, but we also need to see, can we pump up to 10 stories, 15 stories, 20 stories? What kind of mix do we have? What is, and that should be able to go in there. So the rheology really is about these three factors, Flowability, if you're doing, we have concrete, which we call as self-compacting or self-consolidating concrete, which means when you pour the concrete in the formwork, it gets into all the nooks and corners of the formwork, and you do not have to place any vibrator to make the concrete, go into those spaces, right? So it is a self-flowing mix. So that's where flowability comes into the picture. So if you look at these three parameters, majorly the rheology parameters, revolve around these three: workability, flowability, and pumpability.
Sir, what can go wrong if drying shrinkage is high for high grades?
what can go wrong. Well, it's not about what can go wrong directly in the mix itself, but it's more about what kind of precautions need to be taken. Really, I mean, what kind of precautions need to be taken is also dependent upon the ambient temperature and the conditions. Are you working in cooler temperatures like today's, or are you working in a 40 degrees, open atmosphere and you are pouring a slab, right? What happens? Concrete has a tendency to shrink. If it is going to shrink by itself, then it is going to cause random cracks, which are called shrinkage cracks, right? When shrinkage crack comes and they are not attended to, there's loss of durability in the longer terms, because if moisture enters those spaces, it is going to reach reinforcing steel, and there is going to be some oxidation that is going to take place, and you're going to have corrosion, that will start over. So that's when your drying shrinkages are high. What do you need to do? Again, take into account the ambient atmosphere, the humidity and the temperature into place. As soon as concrete gets into a plastic stage after pouring, see if there is a possibility of slightly, not even sprinkling, misting. If you can mist the concrete a little bit over, that's one thing that you can do, so that the evaporation of water, why shrinkage happens? Water evaporates, right? Water evaporates not only due to temperature, but due to the wind also. So what you need to do is either compensate for that evaporation or to stop that evaporation. So you can mist a little bit. Then what you can do is you can put plastic covers during the initial stage, and then thereafter you can do water curing, which, there's nothing like water curing. You pond the water basically over concrete so that it compensates for the evaporation loss, right? The other way around, a lot of places in the world and even in India on certain projects, curing compounds are used. Now, what is a curing compound? If you can mist or spray something called as a curing compound, it's a chemical. That chemical, if you spray over fresh concrete, then it forms a layer over the concrete which prevents the evaporation of water from inside the concrete. If there is no evaporation, there would be no shrinkage. So those are some of the parameters that need to be taken care of, so that you don't go have those random cracks which come up, because then you got to take care of them.
Sir, what is the highest grade you designed and supplied, and what are the challenges you faced?
So, well, there are two phases of my life, right? One being purely as a structural engineer, and the second now, into ultra high performance concrete. So as a structural engineer, and when we look at concrete, yes, I've used all the way up to 100, 110, I've specified, used, of course, the M80 grade that we spoke about a little while ago. We did that years back over here. But in the US too, I did about 100, 110 on a project in 2006. That is concrete. When it comes to UHPC, we are doing anywhere over 150. We are doing 200. We are even supplying at places as close as 230, 240 MPa. It reaches there. We call it M200 mix, but it will reach 240, 250 MPa, So what are the challenges with that? Well, if you have a good design, if you have a good team, right? As a structural engineer, I want to work with a good concrete technologist and good concrete supplier who has a good concrete technologist, so that we can achieve those kind of mixed designs, right? It's difficult, right? At the moment, in terms of concrete, we are using a M95 concrete on a project, Yes, it is tough sometimes. The challenge being sometimes the right aggregate is not able to, reach on the site in time, very difficult to find the right aggregates for that. Those kind of challenges remain. Otherwise, all other things are in place. When it comes to UHPC, I mentioned one thing, that the coarse aggregate is completely negated out of the picture. So that problem goes away, which means we have eliminated the problem of coarse aggregate. So when we do that, automatically, we are just concentrating on the other raw materials plus the sand. So it's technically not that difficult for us to reach very high strengths when it comes to UHPC. But as far as concrete, reaching 95, not a problem, but you have to be really dependent on good quality aggregates.
So what is the role of ultra fine SCMs in high grades?
Interesting. We spoke about some SCMs before, which is like fly ash and GGBS being used as replacement for some percentage of cement, right, to reach these high strengths and in the longer term. They also help with durability, by the way. But now we talk about ultra fine SCMs, ultra fine fly ash or ultra fine GGBS. There's a different perspective that comes into view over here. The ultra fine SCMs are reactive in nature. That means they are going to help in pushing your strength up. And one of the earlier, SCM that was used, or that is also being used currently, is the Micro Silica. There are two aspects of it. Micro Silica doesn't not only pushes your concrete strength up, but because it is extremely fine and has a very, very small particle size, it pushes your durability also up significantly. Now, there is push in the market saying that you can replace 100% of microsilica with these other SCMs like ultrafine fly ash and ultrafine GGBS. As far as the strength perspective goes, yes, that appears to be fine, more or less fine. But as far as the durability perspective goes, just because microsilica is much finer than ultrafine fly ash and GGBS, some amount of microsilica still helps to push up your durability better than GGBS and fly ash.
So what is your take on synergy of high-grade concrete and reinforcing steel in high-rise construction?
Paraji, you just touched the nerve right there. ऐसा है कि if you look at concrete, it's a material which is great in compression, right? And, not so great in tension, right? It can take a very minuscule amount of tension. There's the difficulty, and that's why you put reinforcing steel into concrete so that it can take tension. Now, what happens if you add reinforcing steel just to take compression? It's very difficult. You start adding volumes of reinforcing steel and you start adding a lot of cost. Not only that, you create difficulty with construction and constructability, so as to speak. Let's say you take for a column, for example, out of 100%, let's say, of concrete, if there is 1% steel, vertical steel in it, or reinforcing steel in it, it's very easy to construct. You make it 2, still fine, okay? It's okay. You started increasing the cost though, right? Now, if it starts touching 3% and 4%, you have started making life very difficult for the guys on site, right? And you have started making life difficult for the developer also, right? Because you have started increasing the cost like crazy. The idea is that once your load carrying capacity, you look at your load. If something, works with M30, fine. But if it doesn't work with M30 in terms of just taking the vertical load and you have to start adding steel to it, instead just go for an M40 or an M50, right? And reduce your reinforcing steel percentage from 4% to 1%. It's a very, very easy science. Doesn't cost you much. Increasing the concrete grade doesn't cost you much, but increasing the percentage of reinforcing steel costs a bomb. You do not want to do that. That is a big advantage of concrete. So when you want to take vertical load, increase the concrete strength. And one more thing, in today's modern construction, as you keep increasing the number of stories, you do not want to go to the old ways where, you had a larger concrete column below. Then after 5 stories, you're decreasing the column size. Then you're decreasing the column size. You know what you're doing with that? You're changing the shuttering. You're changing the shuttering in the formwork systems, and it's costing you a whole lot. Instead, what you do is start with a higher concrete grade below. Maybe you need to start with M70. Then as you go up, the load goes down. You go down the concrete grade to M60, M50, M40, probably close it over, have the same column size, same formwork, go up. That is the synergy of high grade. You want to start at the bottom with reinforcing steel. Keep your reinforcing steel in concrete columns to a minimal and work with higher grades of concrete.
So how do we tackle brittle failure and fire in high grade concrete?
Interesting question. As the concrete strength keeps going up, we talked about a beautiful, theory in terms of the physics and the voids in concrete, in the earlier episode, that lower the void, higher the strength. But what really happens as the void goes down, as the void goes down, you lose the space to release the steam in case of fire. Okay. And when you start losing that space, what happens in fire? You might get an explosive failure. So what do we need to do? When we talk of higher strength concrete in the range of maybe 75, 80, 90, 100, you need to add certain kind of, fibers, maybe polypropylene fibers, maybe some glass fibers, maybe some PVA fibers. What kind of fibers? The fibers that will probably melt somewhere close to about 200 degrees Celsius and will create the path for the steam to escape. Okay, because if you don't have a path for the steam to escape, you will get an explosive failure. So you want to basically eliminate that from high-grade concrete. So it has to be remembered that it's not like you're making a 9500 grade concrete and you don't add anything to it. In fact, you're creating a problem with fire. You want to tackle that. Second thing with, the brittle failure kind of thing. Again, because the voids are lesser, the concrete gets brittle and brittle. So if you end into a failure condition, you might actually get an explosive failure again in compression. There too, the ideology is that some of the fibers, whether the fibers that I just mentioned or even steel fibers, a small percentage can help eliminate the explosive failure. The failure might still be, slightly brittle in nature, but the explosive failure will go out. The thing is, the facts are, for those very technically inclined, if you look at a compression stress strain curve of a low strength concrete, you go up to some peak and you have a little bit of a ductility even in concrete, in failure, little bit of a ductility. But as that strength goes up, that ductility gets reduced. So your strength is going up, but the ductility goes down and the brittle nature comes up. So one has to be very careful. You take a cube or a cylinder of M80, put it on a compression machine and you try to push it to failure. You got to put some protection around it. Otherwise, at failure, that cube or cylinder will explode and the chunk of concrete will really fly out. It can fly out as much as 50 feet. So you want to take care of it. So as I was speaking about fibers, right, it is also important that if you're adding glass fibers, as some measure to your high strength concrete, be sure to remember, please add alkali resistant fibers. Why is a simple question. The chemistry is important. Concrete is all about chemistry and you do not want these fibers to degrade and eliminate themselves and be almost like non-existent or non-performing in the future. So please use alkali resistant fibers. Do not just go for cost and go for any kind of glass fiber. Use alkali resistant fibers.
Sir, is high strength concrete synergetic with pre-stressing steel?
Wow. So pre-stressing, let's go back to history a little bit. And if you look at it, it was just very close to right about the independence when the first pre-stress bridge in India, was constructed. First time in the country, was done in collaboration with a French company. It took 10 more years for the second pre-stress concrete project to actually come into India. And today, the whole scenario is different. The simple philosophy is concrete can take good compression. So you add these wires or strands that we call, you put active force and compress the concrete a bit so that when the tension comes, this extra compression is negated. Now, by doing that, you are helping to reduce the quantity of concrete. You are helping to increase the spans, between your columns. There is a great amount of advantage that if you look into literature, you will find with pre-stressing. So high-grade concrete, again, is a great friend of pre-stressing because you can add more pre-stress, right? The lower the grade of concrete, the lower the pre-stressing you can add. The higher the grade of concrete, higher the pre-stressing you can add, and you can get all the advantage of pre-stressed concrete. So, more in the literature with regards to that, there's so much I can talk about it.
Sir, now we have come to, again, my favorite segment of this episode too with you, which is the Mythbuster. I have one more myth. I would like you to bust it for us and for our viewers. Any steel fibers can be added to high strength concrete. Is it a myth?
So in some ways, I can say, oh, that is not a problem. You add something, to concrete, you can add something. But is it giving you the value that you want to add concrete? So let's clear that up. Let's not just say we can add anything to concrete, right? Concrete is an engineered product. It is an engineered product. Let's add the right kind of fibers to it. So what are the right kind of steel fibers that can be added, or what is really necessary? One of the things that is important is the aspect ratio of the fibers, which is the length to the diameter ratio. That is very important. These fibers help in giving some tensile property to the concrete, and therefore they are used quite a bit in industrial flooring. They are also used in concrete in tunneling. You got to be careful about what kind of fibers you add. Plus, you just cannot add any quantity. If you add very low dosage, you're not going to get any benefit out of it. Concrete has a property in tension that it is brittle in tension too, right? But adding the fibers, you can start creating ductility in tension, and adding certain kind of fibers, you can start getting a behavior what we call as a strain hardening behavior in concrete. That means you can get a lot more energy dissipation out of concrete. You can get multiple cracks, and the energy dissipation is really high in concrete. That's a beauty of FRC, fiber reinforced concrete. It has to be an engineered system, so it's not like you can just do anything. We have to pay attention to the engineering of how and what kind of fibers have to be added and take advantage of it to the fullest.
Right. So thank you so much, sir, for your time today. And we have had a wonderful conversation. I would like you to tell us and our viewers, how do you feel about this initiative from Nuvoco?
See, ultimately, it is all about awareness, right? We are all busy in our regular business, so as to speak, right? If we don't mentor and if we don't make our engineering community aware of the nitty-gritty of the systems that wouldn't come in the normal course of action, how will they learn? So I think this is a great platform that you have actually created over here, through which awareness, can be spread. So great going.
Thank you so much, sir. Thank you so much. And we have a very little token of appreciation and love for you from Nuvoco.
Oh, thank you so much. Appreciate it. Quite a bit.
Thank you so much for your time, sir.
Thank you.
Thank you.